All right, first, one administrative thing. I was at office hours today and I saw someone was waiting for office hours for this class. But by the time I got to them, they were gone. So if I missed you, I apologize for that. I normally try to take people in the order that they come in, but I've got two classes. So I'm switching back and forth between those, trying to get to people in the order they arrived. And the C class, my other class, was pretty busy today. And that meant getting to students in this class was a little slow. So if you're the person who showed up and nobody answered your question, I'm sorry about that. Normally, I should be able to get to everyone who shows up. All right, let's go ahead and talk about, so just thinking ahead, a week from today, we have our exam, our first exam in class. I've posted materials for that. And like I've said, I hope to post one or two more semesters of more recent exams for that. Sorry, my phone is ringing. And I hope no one can hear it because it also rings on my computer now. Now I don't know how to stop it. But I hope no one else can hear it and I'll just try to ignore it. I apologize for that bad start to class. All right. I started to talk about the exam that we've got a week from today. I've posted some materials and I hope to post a couple more, one or two more semesters worth of exams that you can use as examples. I think in this class, they've always tried to use the previous exams as a study guide, as a way of seeing the kind of questions we're going to ask you. This exam for this semester will be different, but I imagine a lot of the questions will be similar kinds of questions. So feel free to look at that. It's posted kind of down near the bottom of our Moodle page. And I know I've mentioned that a couple of times. I'll go ahead and say the exam, since I've got everyone listening, hopefully, the exam starting next week will go from the start of the day on Wednesday till, so that means 8 o'clock Wednesday morning until 5 o'clock Thursday afternoon. So kind of start of the working day to the end of the working day. Just be aware of that and be aware that that's Eastern time. So don't let a difference in time zone cheat you out of exam time on that. Any questions before we get started? We got a couple of topics we're going to talk about today, mostly in the area of efficiency. What can you do to write a small or fast, especially small assembly language code? So we'll get some tips about that. We'll see one more system call for printing out strings, and just a couple of little miscellaneous topics. Oh, I apologize. I look at all of these before class to make sure I'm ready. But then sometimes if I look at them too early, I don't always remember the slides when it's time to talk about them. So here we're showing a implementation of a for loop. The for loop's up at the top, so it's easy to think about it in a higher level language. So there we're just counting down from 10 to 1. And at the bottom of the slide, we're showing how we might implement this, or in the middle, how we might implement this in assembly language. We're starting AX out at 10. Then we do some stuff. We're assuming we have something to do on the body of the for loop. So that's what I mean by this ... here. And then for the next iteration, we need to decrement I. And then you remember we talked about these last time. This is a conditional jump instruction. I would read this, and I'm just talking through how you can remember this. I would read this as jump if above. So reading this subtract, and remember a comparison is really a subtract instruction without saving the result. So this is the same as a comparison. Or you could say, I'm doing the subtract to decrement what's in AX, but I'm also getting a comparison against 1 for free in a single subtract operation. So this will jump if AX is above 1, or if it was above 1 before we did the subtraction. So it'll go back to the start. And I don't want to talk, made a big deal about how this loop is written, but I want to talk about checking for whether that subtraction works or not. In the past, we've made a big deal about whether we need to check for something like overflow. Here's a subtract operation and we're doing a jump, but it's not tested based on overflow. Do we need to worry about overflow in the case of this subtraction? And I guess here I would say we're okay without worrying about overflow. It's worth thinking about. But since we start AX out at 10, what could and then we're subtracting a positive number from it. What could cause overflow? Well, we'd have to subtract so much from it that it would become negative. We'd get, or drop below 0 and we'd get overflow if we're thinking of it as a unsigned value. And since we bail out of the loop as soon as we drop to 0, and we're only subtracting one at a time, we shouldn't actually have to write code for overflow detection for that. This is the kind of thing that's normally not done at all in a higher level language. Normally something like Java or C or C++, they depend on the assembler writing that out in meaningful assembly instructions. Sorry, they depend on the compiler doing that. And they depend on the programmer picking types that are wide enough for what they have to do. But they generally don't build in tests for overflow. And if they did, they couldn't be as smart as we're trying to be right here. Since we have access to the underlying assembly, we can decide when we have to worry about the possibility of overflow. We can put in instructions for that if it happens, or kind of like we've argued here, we can decide in cases like this where it couldn't happen, and we can leave those out if they're not needed. This is in that area of assorted topics. For the next programming assignment that you're going to do, you're going to be writing a program that reads keyboard input. And I wanted to make the point, I think this is already made in the assignment, that most normal keys return a single code from the operating system. We saw last time the system call that you can make to get a single key worth of input from the operating system. And normally when you press a key like a letter or a number, you will get the ASCII code for that character. But there are some keys that will generate a 2-character code when you do that, like when you press a function key, or if you press the home key, you'll usually get a 2-character sequence. You'll get a 0 back the first time you call it, and then you'll get some code that indicates what the key is. And that's just to support keyboards that have a lot more keys you can press or a lot more symbols you can generate than we have in the ASCII character set. In this case, when you get one of these 2-character sequences, you'll have to make 2 calls to the operating system to get both of those characters. For something like a function key, you'll get a 0 for the first character, and that'll tell you that it's a special key, and that you need to make another call to get another code that says that indicates what the actual key is. On the topic of peculiarities from the operating system that we're working with, you know that we're working with kind of an old operating system that's been around for 30 years, more than 30 years. And it represents a time when we were kind of in the transition from 16-bit to 32-bit address spaces. And that's why we have weird things like the segment registers to let programs access more memory using only 16-bit offsets into a segment. Another peculiarity you'll see is the way DOS interprets, or the way it handles end of string. You probably noticed this in the Hello World program, whereas a normal C program and a lot of languages at the same low level depend on null terminated strings or a null terminator marking the end of strings. For the operating system, DOS depends on a $sign for that. So if you want, and you saw this in Hello World, it was kind of like the data here at the bottom. If you want to define a string along with an end marker for the operating system in your data section, you can define a sequence of bytes with the contents of your string. And if you want line termination at the end, of course, you remember that's a 2-character sequence in DOS. So there's a carriage return line feed characters, and then a $ to serve as an end of string marker. Again, nowadays, in a language like C, we would be using a null for that. When you're telling the OS that you have a string you want it to print out, $ is how it expects you to mark the end of that string. How do you tell the operating system that you want it to pick out a particular string? Well, there's one more system call like the ones we saw last week. You can tell that looking at the code over here. It's got a call to interrupt 21. So that's the same interrupt that we would raise when we wanted to read a single character or write out a single character. Before we raise that interrupt, we tell, or we get ready for the OS to be able to tell what system call we want by putting a value in the high part of the AX register. So this 9 says, I want you to print out a string. That's different from the 2 we saw last time. So we'll have to remember 9 means print out a string. And then the only other thing it needs is, where is that string? It's going to expect it to be in the data segment. So I just need to give it the offset of the start of my string in the data segment. And it's expecting that offset in the DX register. And just like when we introduced segments, what I mean by offset is how far is the start of that string in the data segment. So I'm going to load the offset into the DX register. And again, that's like a parameter for the system call. When the OS wakes up after this interrupt 21, it's going to look at AH and say, oh, I see you want me to print a string. It's going to look into DX to know which string we want. And here's where we give it the offset. I don't think we've really talked about this syntax yet. You can see MSG is the name of the start of this part of our data segment. So that MSG kind of means the start of this sequence of bytes. It's like a pointer pointing at that A that we defined right there. Why did we put offset? Normally when we use something out of our data segment, we just put square brackets around it. And that means get the thing at this location in my data segment. And the reason is that thing I just said is not what we want to do. If I put MSG inside square brackets, that would get the contents of memory starting at MSG. So if I was getting a bite-sized piece of data, that would give me just the value of the ASCII code for A. If I was getting a word-sized piece of data, and DX is word-sized, that would give me the code for these 2 characters. Well, it's a detail, but the code for this B would be in the high order byte of DX, and the code for this A would be in the low order bits of DX. I know that seems backward, but it's because of the byte swapping. If these are the sequence of characters in memory, then if you go tell the processor, go get a word starting right here, you're going to get these 2 bytes, but it's going to byte swap them as it brings them into the register. Or I guess I'd prefer to say it's going to put this byte in the high order part of the register, and it's going to put the byte for A in the low order part. So I got this halfway said. I was trying to convince you why we wouldn't put square brackets around MSG. We don't want the thing at that location in memory. We kind of want a pointer to that location in memory. It seems like we ought to be able to just say MSG. If MSG inside square brackets evaluates to what's in MSG, then MSG by itself seems like it should evaluate to the start of MSG or whatever offset it is. But the way you have to say that is you have to put the word offset in front of it to make it clear. I want the location of MSG within the data segment. So it gives, if MSG is the first thing in your data segment, then that's going to be I want to say it's going to be at offset 0, although there may be some stuff earlier in the data segment that we don't control. But either way, it'll tell you how far this thing is allocated into the data segment. We'll pretend I did a good job explaining that. This picture helps to show what gets passed to the operating system. So when this gets loaded into DX, the offset, just like we've been saying, the starting location, the location of this A in the data segment gets loaded into this DX register. And then just like printing a string in C, the OS is going to go through memory starting at that offset in the data segment register, printing out each symbol to the DOSBox window until it hits the $. And that's where it's going to stop, just like a C program would stop at a null terminator for a string. Oh, I started to say a moment ago, this instruction, this move offset of MSG into DX, what does that get assembled down to? Well, it's really the same as moving any immediate data into DX. When we say to the assembler, oh, just give me the offset of MSG in the data segment register, the assembler can figure that out. It did the layout of all of that data in the data segment register. So this assembles down to an instruction that basically just says, put this number into DX. The assembler figures out where it's going to store this, or where it does store this MSG section of our data segment, where MSG starts in our data segment, and then it just loads that, or it writes a machine instruction that loads that offset, loads that value into DX. What if we forgot the $? And this is a common mistake in C, to forget the null terminator on a string. It seems like this would be an easy thing to do. What's going to happen? Exactly the thing that would happen in a C program if you forgot the null terminator. The operating system doesn't know where your string ends. It's counting on that $, to tell it where to stop. So if you tell it to print starting at this location of this A, this 41, it's just going to keep going through memory looking for a $. Maybe there happens to be a $, later in memory. Probably there will be somewhere, but it's going to print all the characters up to that. And failing that, it's just going to keep running through memory, printing out characters one after another to the terminal until you kill the program or reset the computer or pull the plug on it or something like that. So I guess worse than a C program, if we can trick the operating system into getting stuck in an infinite loop, then we may not just be able to kill a process, we may have to shut down the whole computer. Looking at the contents of a string in memory, we can think about how does this compare to what might be in a file. And this is made a little bit more complicated because what shows up in a file when you start typing stuff depends a little bit on your text editor. And that's what I'm kind of showing here. Let's pretend you brought up a text editor and you just started typing in the contents of a file. So up here, we're showing here, but let's pretend this is the sequence of keys you pressed. So you typed 1, 2, and then a space. And that kind of explains, and let's pretend this is what gets stored in the file, or let's say that's what I'm trying to show here. So when you type the 1, well, in your file, the ASCII code for 1, and in hex, that's a 31, got written into the first byte of the file, or it got probably written into memory, and it's gets saved out to that file when you save it. And then when you type the 2, the ASCII code for 2 went next in the buffer for the file, for your editor. And then when you typed a space, the ASCII code for a space went into the buffer next. And then if you kept typing, if you typed a capital A, that's a 41. And when you hit enter, if this is a DOS editor, then it's using Windows style 2-character line termination. So even though you only hit one key, enter, it's going to put the 2-character carriage return line feed into the buffer, since that's what an end of line marker looks like for DOS. And then if you kept typing, if you typed a lowercase a, that's a 61 in hex. and then a space, and then a digit 9, that's a 39 in hex. And then if you hit save, what's going to happen? Well, there especially, it depends on your editor. And probably you saw this in C class. I didn't hit enter, at least according to the script up there. I didn't hit enter after that 9. But lots of editors will automatically put line termination at the end of the last line, even if you didn't hit enter there. They'll say, kind of like we said in C class, every line of text should have a line terminator marking the end. So even though you didn't ask for one here, your editor might go ahead and put the 2-character line termination sequence there typically when it saves the file. I checked in C class a few semesters ago, and not every editor handles this the same. Some of them, and I think, not that it matters here, but I made a little list of which ones seem to do it one way or the other. So normally, your file would end right there after the line terminator. But this is another peculiarity of DOS. For text files, it uses an extra character at the end to make it easier to detect the end of the file. And that's what this 1A is. I know when I teach the C class, I feel like I say over and over, there's no end of file character. When you're reading input, something like getchar will let you know when you've hit the end of file, but there's no character sitting at the end of your file saying, I'm the last character. And imagine my embarrassment when I saw that DOS used to handle it this way. So for text files, depending upon your editor, they may automatically put in a 1A at the end, marking the last, or really marking the end of the file. For me, I think of the file as, well, it ends right there after that last character, and this is just a convenience for telling where the file ends. Modern editors, I definitely wouldn't expect that kind of behavior. If you look at the ASCII character table, this is in that non-printable region, or the region of control characters, the ones up to hexadecimal 20. I don't remember what this one is specifically. It's not called end of file or anything like that, but as a text file, DOS is often writing out this extra character at the end of a file. So if you created a file like this, the behavior that you get could vary a lot from system to system. And that's kind of, we saw the top example of this on the previous slide. You type the same thing, I think it was 1-2 space, A, carriage return, space, or so carriage return lowercase a, I think. Yeah, lowercase a, space 9, and then save. If you're on a real DOS system and you run an editor, it's probably going to type that in with Windows style line termination and with this extra character in the end, helping to mark the end of the file. If you did this in an edit program on DOS, you'll probably get the same thing, except no extra end of file marker character at the end. If you're a Unix user and you fire up plain old Vim, you'll see two differences. You'll see Unix style line termination. So you'll remember from C class, on a Unix machine, Unix, that includes Linux and Mac machines that are variants of Unix. Whenever you hit a new line, you get a single character line termination, just the line feed character \n. So your line termination will be a lot shorter. If you do this in Windows on WordPad, you'll see similar behavior, except differences in that last line. I mentioned on the previous slide, editors, some of them automatically will put a line termination at the end of the last line, and some of them don't. So there are some editors that, like I guess WordPad, that don't do that automatically. I didn't try out WordPad when I was trying this for C class. Questions? So this is just if you had to generate a text file, or if you think about what happens in an editor, this is the kind of thing that you might expect. And from one particular editor to the next, you could see some differences. But all of these behaviors, I think we can explain even if we see some variation from one to another. Oh, this is talking about as you start writing your own assembly language program, and as you start trying to make sure that your output is right. From the tools assignment, you got to play with a couple of programs that let you look at the contents of a file in hex or let you compare the contents of two files. And we're listing, I think one of these was on that assignment. There's a compare file command that's provided with the samples from DOSBox. The samples that you used on that tools assignment. You can give it any two files and it'll compare their contents and report the first place where they differ. There's a command that will look through the contents of a file and look for line termination and the end of file character. There's a test file program that'll look through the contents of a file and will print out the hexadecimal code for every character in that file, including special characters. So if you had a text file and you wanted to know which of these behaviors you were getting from your editor, this test file program should be able to show you exactly what's there in that file. All right, so we said we were going to talk about a couple of things today, mostly efficiency and assorted topics. And we mostly been talking about assorted topics so far. What do we have to say about efficiency? For us, efficiency is going to be writing assembly language programs that are, this will be circular, but I'll fix it, that are as efficient as possible. So we care about assembly language programs. What do we mean by as efficient as possible? Well, using as little resource, using as few resources as we can. And the resources we normally care about are things like size. That could be the size of the assembly language source code itself. In general, a shorter program is a better program. It's going to take less memory. It's going to make better use of the cache. And it's arguably not going to have extra instructions that it doesn't need. So the size of the program itself might matter. The size of the memory, the temporary storage that the program needs, the data section of the program might also be something that we care about. But realistically, we're mostly going to care about the size of the source code. What are really the number of instructions in a program, not necessarily the comments or other things like that. What else could we care about for resources? Well, often we care about execution time. And you know from your data structures class and probably your previous classes, we usually look at that asymptotically. We look at big O notation for the runtime. And we'll care about that in this class, but we'll probably look more at program execution size. In the real world, we often care a lot about resource use in terms of programmer time. So as long as the execution time or the memory used by a program is tolerable, sometimes how long does it take to develop and test this program is a lot more important than, do we have the smallest source code we can have? Do we have the absolute fastest execution time we can have? As far as grading things in this class, I guess we don't get to look at programmer time as much as we might in the working world. In practice, how long it's going to take to solve a problem ends up being, or how long it's going to take to implement a solution a particular way can end up mattering a whole lot. Now, we can compare some of our favorite implementation languages in terms of their overhead, in terms of the size of a solution in these languages. We've got assembler, we'll say your new favorite implementation language, or at least one that's new to you. Java in the middle, which you're probably most familiar with if you came through our program. And over on the left, it says C++. I know you haven't seen much C++, but you've probably seen a lot of C. And that program, even though it's C++, it's only using C features. So we can think of that as a C program just as well. What do these programs do? They do nothing. In fact, they do nothing in all three of these languages. In C or C++, we can just make an empty main function. In Java, now there's a little more decoration for the main function, but it's essentially the same thing, a main function that doesn't do anything and returns right away. In assembly, we've got to do a little on our own. Just to ask for our program to exit, we've got to ask the operating system. We have to make our own call to exit, at least for DOS. So it takes these two instructions. This last one you already know, it's not really an assembly instruction, but it tells the assembler, here's where my program starts. So those two instructions are really the body of our program. So it kind of looks like C is the shortest, and Java is pretty big, but pretty simple, and assembly is probably the most complicated. But we see something different when we assemble these programs. If we assemble that assembly language program that does nothing, it compiles down to a 5-byte program. It's really just the assembly code for the two instructions we just looked at. The load this thing into AX, and that'll be a 3-byte instruction, and then raise interrupt 21. That'll be a 2-byte instruction. How about the Java? Well, the Java is going to compile down to a Java class file, and for that one, I've got a thing that disputes this in a moment, but I got 238 bytes when I compared it, but pretty close to the 236 reported in, 236 reported in this table. If you take that C program and compile it on a Windows machine, you'll get around 7,500 bytes. Why so much? Well, the C program contains everything it needs to run. It just has to get loaded into memory and executed. And even though the Java is a lot smaller, to actually run it, we've got to fire up a Java virtual machine to make sense of that Java code. Any of that overhead is packed right into the C executable. And that makes the executable carry a lot more of that around with every program that you write. If you did this on a Unix machine, it was reported that that's going to cost you around 24,000 bytes. I gave it a try myself right before class, and it wasn't that bad for me. I tried it out on a Linux machine, just an empty main program, and it's in line with C or C++ on Windows. And like I said, I got a little bit more expensive of a program when I tried out Java on a Unix machine, but pretty much the same as what's reported there. Yeah, sorry, I'm making sense of this slide. For your first project, you're going to be writing a program that reads key presses by the user and reports them as or does some translation with the keys as the user presses them, and then reports those. We can write the same program in a couple of different languages. If we write that program in assembly versus a similar program written in C, we can compare overhead by comparing execution time. That's maybe a little unfair for this program because it's going to spend most of its time just waiting for us to press keys. And unless we can press them really, really fast, the program's execution is the time elapsed for execution is mostly going to be it waiting on us. So another way we could measure execution time is we could count machine instructions. And here you can see that being willing to code at a lower level in a language like assembly language can give you much cheaper execution, especially if you count individual instructions. This program written in assembly for a particular sequence of key presses, we only executed 20 instructions start to finish, whereas even in a low-ish level language like C, writing similar code and compiling it down to machine instructions still gave us a lot more instructions that got executed given the same sequence of key presses. This is not exactly the same thing as time because we're just some instructions could be more expensive than others, but you can see if we're willing to control what instructions the processor can execute, then we can come up with a much more efficient program than you would get even in a low-ish level language like C. So this is some of what you're going to get to think about on your programming assignments. For the first assignment, the one I mentioned where you're going to be getting key presses from the user and outputting characters based on those key presses. You've got an efficiency target that measures the number of instructions your program uses. There's a document posted on our website that says what counts as an instruction. For instance, the data declarations don't count as instructions. Those are just messages to the assembler when it prepares the data section of your program. The comments don't count as instructions, but things that assemble down to real CPU instructions like compare or add or all the conditional branch instructions that we talked about, those will count for your efficiency target. For efficiency on this program, to get 20% of your grade will be dependent on how efficient you are, where efficiency measures number of real instructions in your solution. And this table shows how that'll get calculated. So if you can write your solution in 20 or fewer machine instructions, then you'll get full credit for that. If you need a couple more instructions, then you'll lose 5 points out of that efficiency part of your grade. If you need a couple more, that'll cost you 10 points out of that section. If you need somewhere in the mid to high 20s, that'll cost you between 15 and 20 points of the efficiency part of your grade. So this is to help you think about the stuff that would matter if you're switching to assembly language programming, even for part of a bigger implementation. Let me try to say that again. If you write assembly language as a working programmer, you're not going to write a whole lot of it. You're going to do much of your programming in higher level languages, and you're only going to program in assembly when you really need to. And one reason you might really need to is there might be little sections of your program that are performance critical. And for those, if you're bothering to go down to assembly language to write that part of your program, then you're going to want to think carefully about how to make that part as efficient as it can be. If you're bothering to program in kind of a hard implementation language, like assembly language, then it's worth it to have, to be able to think critically about what's going to be more efficient. Questions about this part of the next project?
I had a comment on the previous for compiled size. I actually did test it just now. The smallest I was actually able to get, the empty, at least on my system, was down to like 13K or so.
Oh, for empty
for the C++.
on Linux?
Yeah.
Huh.
I'm not sure if there's anything else that's being linked in by default. I'm just using GCC. I'm fairly certain there's a bunch of other libraries you can force it to just not include, but I'm not sure.
I mean, so I'm not lying to you about this number, although it's possible I made a mistake. You said 12K?
Smallest I got it was 14.
14K?
Technically like 13.7-ish, but basically 14.
Yeah, and mine's about 8K. I don't know what to tell you about that. I did it on a Ubuntu machine. It might just be version of the compiler or some parts of the C library. Then might, maybe they change part of that and it's got a different fixed size footprint. Thanks for reporting that, though. It's interesting to hear. I did not try to reproduce this, the assembly on Windows. We could give that a try by just writing this program and doing it on DOSBox and then assembling it with our assembler. That 5 seems, even though the instructions would assemble down to that seems smaller than I would expect. I would still expect some overhead, even if you didn't really have a data section. But maybe it is just really those 2 instructions. Anyone else? All right. When I switched to the slide, I wasn't sure what this meant, but after staring at it a moment, it just means we're only looking at the size of your source code, not how many instructions actually get executed while it's running. So the like back here, we were talking about how many instructions actually got executed on a C version or assembly language version of this key program. And here we're just saying that you don't get charged for number actually executed. So we won't be looking at that on this assignment. So for reasons like this, so I tried to sell you on here's why trying to think about efficiency matters. And I tried to sell it in 2 ways. I said it matters because it's part of your grade. And I said it matters because if you're bothering to program in assembly language, the little bit of code that you're going to write in assembly probably is going to need to be as efficient as it can be, or it might as well be as efficient as it can be. There's no fixed set of tricks for making your code efficient. If you look at optimizing compilers like the GCC compiler, it's got a giant list of tricks it can do to try to make your program more efficient. And you can turn those on and off individually if you need to try to get the fastest code. To me, that says, well, there's not one right way to write something to make it as efficient as possible. But the right way to do something, the right way to organize your code might depend on what you're trying to do. When you're doing an assignment, having working code needs to be your main concern. So there's definitely no reason to sacrifice correctness for efficiency. There's chapter 23 of the notes for the class, and that's on the reading list for the next exam. So you might want to go ahead and have a look at that as you're starting to write some assembly code. It has some hints for making your code more efficient. And this is the kind of thing that you can talk with the teaching staff about, maybe during office hours, if you've got some good ideas and you're trying to make them work or you're not sure why they're working. I just said there are no hard and fast rules about what you can do, but there are some good ideas that show up more than once. So I'll show some standard things you can think about, or I guess things that if you see yourself doing this in your code, there are some quick things you can do to shorten your code or make it more efficient. So for these, we'll talk through what they're doing, and then we'll talk through what's wrong with them, which usually will be pretty easy. And then we'll talk through what you can do to fix it. So here we've got, let's pretend we got a character in the low part of the AX register. We're seeing if it's dot. If it is dot, we're going to exit the program. Otherwise, we're going to print out the character and then maybe do something else. So we're pretending there's a label exit defined elsewhere in our code. If we don't exit, we want to print. So we got a label for print. And if we don't exit, we just jump to print. And here, I think because of the organization of the code, it's pretty obvious what we could do better. And that is, well, if your block of code that's labeled print is right after this block of code, you don't really need to jump there. So we could take out this jump instruction. I guess the bigger takeaway is this could help you think about how to organize your code. Like here, it's completely obvious. that we don't need to jump to print, we could just fall through to it. If these were in different parts of your code and you were jumping around between parts, that could be a hint that you want to, or that you could reorganize your code. So you could take advantage of just falling through from one section to the next section rather than having to jump from one section to another. And you can imagine if your code is made up of a lot of little blocks, each of them doing a different job, there could be a lot of choices in how you organize them. And some of those are going to save you an instruction or two that would otherwise just go to control flow of control in your program. Here's another example where we've got an unnecessary jump. Here same thing, we're pretending AL has a space, or sorry, AL has a character and we're comparing it to a space. If it is a space, we want to print it. Otherwise, we want to do something else. So that's what this test is. We're comparing AL to a space. If it's equal to a space, we're going to jump down here to print. Otherwise, we're going to jump to some next instruction. We could do better than this. If we change how this jump if equals works. The problem is written as a jump if equals, or let me try to say that again. Let me back up to here. So if we print, we could just fall through to this print instruction, but this jump if equals is the wrong test for that. If we take the jump if equals and replace that to a jump if not equals, then instead of jumping when it's time to print, we could jump when we don't want to print that character. And then again, that saves us an instruction. We get to, on the case where the character is equal to space, we can just flow through into the print. And on the case where it's not, we can use this conditional branch to jump. So again, that saves us one instruction. I'll back up and say, sometimes you have to do this. The range for jumps with conditional branches is not as big as the range of jumps for unconditional branches. So if your program, if you had to jump to a location that was too far away, you might have to code it like this. If, say, next test was really far away in your code. Now that's another reason to be able to write small code. If it's more expensive to jump further away in your code, then all else being equal, trying to make your code short will make it less common for you to have to do a jump that you can't do with a conditional branch. Like I said before, organizing your code so that you can take advantage of the flow through. So instead of having to jump from one block to another and then jump back, having it so that you can commonly execute one block and then just flow into the next block is going to not only make your code faster, it's going to let the processor do a better job of branch prediction, of knowing what your code's going to do next, but it's also going to make your code shorter and it's going to make it easier to hit these efficiency topics, or sorry, these efficiency targets. So over on the left is what we could call spaghetti code. It makes unnecessary jumps. It compares, so the idea here is it's got a variable val, it compares it with 0. If it's below 0, we're going to modify it. We're going to set it to a particular value. So this is kind of like an if statement where the body is handling values that are less than 0. By the way, I may have said the word below a moment ago, which is a bad choice of words because above and below are special words for 8086 assembly, and greater than or lesser than are also special words. And I think I accidentally used the wrong word there. I notice here this is jump if less than, so that would be for a signed comparison. And that makes sense if we're checking to see if it's less than 0. So if it's less than 0, we're going to handle that as an error case. And here we're pretending we just set it to 1. And then once we fixed that, we can jump back where we were and resume running. So it's kind of like this is an if statement, and this is the body of the if that is going to handle this condition that would otherwise be an error condition. But jumping down to this block of error code is probably some unnecessary jumping. How about if we take this instruction that handles the error case and we just jump over it if we don't need to do that? And that's what this code on the right does. It does the same thing, same comparison, but we change the sense of this jump. So instead of jumping if it's less than 0, if it's not less than 0, if it's greater than or equal to 0, then we don't have to do anything special. So we jump over the move instruction that set it to 1, and then that saves us one jump instruction. And it means that trying to read and make sense of this program is probably a little bit easier because it's more of a top to bottom kind of flow of execution now. So if you feel like you've got cases where you have to jump to a piece of code and then jump back, it's worth it to think, to consider, well, could I reorganize this code so I get more linear flow through the instructions rather than having to jump around. Here we're looking at an example of, I guess, a good practice if you remember it from C, but an unnecessary practice if you think about what's really going on. So here we're getting ready to make a call to read a character. You can see where this int21, we're jumping to a DOS system call. Before we do that jump, we tell DOS, or we get ready to tell it what system call we want to make. So we put an 8 in AH. And if you remember, that's the call to read a single character. Even if you don't remember, fortunately, it's in the comment over here. When this call reads our character, it's going to put it in the low part of the A register. So before we read, we'll clear out the low part of the A register so that it can put the result there. Well, I had to try to sell that way of thinking about this code because that first step, clearing out the low part of the A register, is unnecessary. The OS is going to be able to put the code for the character it reads in AL, whether or not you put a 0 there first, and it's going to override it no matter what you put there. So if this was loading 0 into AL, it would be unnecessary. Here it's even worse because you're loading a 0 into AX. And then you're just going to overwrite the high part of that AX register with the instruction or with the system call you want to make. So half of the work you did up here is going to be overwritten on the next instruction. Question?
Oh yeah, I was, would there be a difference between, so you can do this one byte at a time, but you could do this one byte at a time, or you can do it a single, or you or you can do it to the entire 16 bits here.
Yeah, like we're doing here.
Yeah. So would it still take more processor time, or would it still be less efficient? Assuming you actually needed to do this, would a better way to do it would be to just like say, okay, I'm gonna say 0008 or what, or 0800, whichever way you entered it. Like that would save you a line of code, but would it be equivalent to the processor?
It would not be equivalent to the processor. Let me make the point I was about to make, and then I'll make sure to address what you're asking, because it's really the same kind of idea. So I was going on about how here this instruction is unnecessary, and that was probably obvious to everyone who's watching this. And I made the point that, well, the low part, you don't have to initialize that, and the high part you're about to overwrite anyway. And even if you just initialize the low part, like if you said 0 gets copied to AL, that would be better. It probably wouldn't be better in the scoring of your programs, but it would be a shorter machine instruction. Because if you're moving a 0 into AX, then that's a 16-bit move, which means this 0 is going to be a 16-bit literal value. That instruction is going to take 3 bytes. One to say move into A of AX, and I know we haven't really talked about this. I haven't told you here's how an instruction is going to get encoded, but we've seen some examples of it, and it shows up whenever you run the debugger. It shows you what this stuff assembles down to. So we're going to have an opcode that says, I want you to move a literal value into AX. And then if it's AX, this is going to be a 16-bit value. So that's 2 bytes. If you were just moving into AL, the immediate value would only be 8 bytes. So it would be a shorter instruction. And trying to answer the question I got a moment ago, if the instruction is shorter, then at least on an 8086, it's going to be faster. Because remember, that was, or I guess it was the 8080 was written with a plan for an 8-bit data bus. So if you have to read in every byte one after another, then a 3-byte instruction is going to take longer than a 2-byte instruction. We're not, I don't think we're looking at that in grading your assignments, but if you're really concerned about performance, you might care about that. Modern processors have much wider buses than that, but still, shorter instructions are going to burn up less of your cache space, so they're generally going to be more efficient. Let me know if I didn't answer your question. I know I said a bunch of stuff, and I planned to address what you were asking about. Maybe I skipped over that part.
No, you answered my question, which was, is a 16-bit instruction, is that going to take longer than an 8-bit instruction? That was really what I was getting at.
It's going to, especially if it's accessing immediate data,
yeah,
where the data is encoded as part of the instruction. Yeah, so again, I'll say real fast, you can think of this as getting encoded as an opcode that says, I want you to move something into AX. And then as a 2-byte value that says, oh, it's 0 that I want you to move into AX. And even though we write out that 0 as, it's just a 0, for a 16-bit move, that's going to be 2 bytes worth of 0.
So, yeah, before we move on, I also wanted to, so I guess another thing I was getting at is if this really were necessary, like say you had a conditional below this, like maybe you read something into it and maybe you don't, but you need it to have a valid value in it anyways, or at least a known value in it anyways. What would be the cleanest, what would be the best way to do that? Like, would you load, would it be better to load things into A, L, and AH separately, or would it be better to do it all in one instruction with then load something into AX and just put a sort of like we do with the exit code where we say 4C00H, do something like that?
So I feel like I can answer that. And when I started answering your question, I meant to say that. I guess if you have to initialize both parts of AX, it's better to do it in a single instruction. I mean, that's only one instruction, which is good. But if you think about the way it gets encoded into machine code, let's pretend this was an AL instead of AX. So let's pretend you're doing the low half and the high half. Each of these is going to be opcode and then immediate data. So this is 2 bytes. This becomes a 2-byte instruction, and this becomes a 2-byte instruction. So that's 4 bytes. If you did it all at once, then it's only 3. And I know that that is a little thing, but if you said, oh, I'm going to move into AX and I'm going to do both halves at once, then it's going to take 1 byte to say that you want to do that, and then 2 more bytes for the immediate data. I can double check on that. I'm going based on looking at the debugger and its encoding of machine instructions, and I'm not an expert on how these get encoded.
Well, it makes
but
sense.
I will be by the end of the semester.
It makes sense and it answers my question. So thanks.
All right, so these are just some examples and hints at how you can try to hit the efficiency goals. I know at this point in the semester, worrying about, oh, I got to make my code as short as possible might make you nervous, but just my suggestion would be get a working implementation first, and then plan on having some time to refine it a little bit to try to shorten it and hit the efficiency goals. This is just a detail, just trying to help you think about how math works on the processor, and maybe trying to help you with a potential source of confusion on this. You remember subtraction, maybe day 2 or 3 of class. We made the point that if we have a 2's complement representation, then it makes it easy to do subtraction, or at least we don't have to build separate hardware to do subtraction. Sure, we could build hardware that did bitwise subtraction, and that's what we mean by this real subtraction over here. We could go one, here it's hexadecimal, but we could go 1 bit at a time, low order to high order doing subtraction. And if we subtracted this hexadecimal number from the one on the top, here's what we'd expect. Or on the right, we could take that same number on the top, and then we could do adding the 2's complement. And remember, to detect overflow correctly, we have to do it like this, or this is the right way to do it, to flip all the bits. And then normally we would add a 1, but rather than doing that on this number and then adding it in, that might cause us to miss an overflow when it happens. We need to add in the 1 separately and then add all of these, and this should give us the same answer. But here, if this is the 2's complement of, and you can check, 5550, 2's complement would be, yeah, it seems like it would be AAAF. Or sorry, the flipping all the bits, just the complement would be AAAF, and then adding the extra 1 would be the 2's complement. And then adding that to the same number at the top, supposed to give us the same result over here, but it doesn't. If you work this out, we should get 88000. These are supposed to work out to the same. Why don't they? Well, it's because I was trying to fool you. And I had to ham it up a little bit to try to make it sound like it makes sense. The reason this doesn't work is because of the size of this number right here. Up at the top, I've got what I'm pretending. I mean, I wrote down 5 hexadecimal digits. So I'm pretending that's a 20-bit number. And if you're just doing real subtraction, it's fine to pretend that there's a 0 right here, that you're doing 20-bit bitwise arithmetic, and you just didn't bother to write down the 0 over here, and the subtraction will still work out fine. But if you do 2's complement and you ignore one of these digits, here I only did a 4-digit 2's complement, so that's 16 bits worth of 2's complement. I flipped all of these bits, but really, if I'm going to add this to a 5 hexadecimal digit number, a 20-bit number, then to negate this, I better have the same number of bits. I better have 20 bits. So really, this should have looked more like this. Leaving off the high order 0 over here didn't really hurt anything when I did the subtraction, but ignoring that 0 when I flipped all the bits, well, ignoring it left a 0 there, and it really should have been an F. And if you do the 2's complement subtraction, or sorry, if you do the 2's complement like this with all 20 bits, and then you do the addition, you'll get the right answer. So just be careful if you're doing adding with the negation of a value, just be aware that the 2's complement depends on the number of bits you're using. And here, negating a 16-bit number is going to give you a different result than negating a 20-bit number, even if the low order bits are all the same. And that's kind of what this is showing. Here we're just getting some practice on reading assembly language instructions and making sense of what they say, essentially trying to explain what's going on in an assembly language program. So here we've got a program that's looking at the value of a variable, and it's checking to see what range it's in. And we want to think about, well, exactly what is it checking? What is it checking? We're pretending we've got a variable that is a 16-bit. Well, it could be signed or unsigned. Fortunately, there's a comment here that says, I'm planning on this to be an unsigned value. So it's 0 or positive. The question mark in the initialization says we want this code to work for any value. That's not legal assembly language. We're just saying pretend there could be any initialization value there. What does this code do? Well, it compares that value against 1,000. And then if it, I probably should have read this blue question up here first. What's going to cause this to call hit? And hit we're pretending is a label that gets called based on these comparisons. So it compares it to 1,000. And this is JBE, jump if below or equal. That sounds right, because we said we were thinking of it as an unsigned value up here. So if it's below or equal to 1,000, we're going to jump to hit. So that's kind of like these cases here. If it's 1,000 or below, it'll jump to that instruction. And then we compare it to 100. If it's, so we compare it to 100, and if it's above or equal to 100, we're going to call hit. Otherwise, we're going to call miss. I didn't notice this when I was preparing for lecture looking at these slides, but now I see that this looks like a silly piece of code because it seems like every value is either below 1,000 or above 100. So it seems like in this example, even though admittedly, I didn't think about this when I was getting ready for lecture, I didn't write this example. If just to read it again quickly, if var is below or equal to 1,000, we're going to call hit. And even if we don't call it there, if it's above or equal to 100, we're going to call that. So here, I would say, not even knowing what this code is supposed to do, I would say this looks like a bug. I don't know if there's any reason to have a series of tests where the result of the test is always true. Sorry for my figuring this out as we were talking through it. This is kind of like in a higher level language, if you were writing a condition and you got the and the or backward. And certainly meeting with students, I see that kind of thing a lot. It's maybe even easier to make that kind of mistake in an assembly language program. Here's another example of the same kind of example. So let's pretend we had this assembly language code. What's going to happen when we try to run it? In particular, we're using the 8-bit AL register, kind of like a counter. We're going to start it out at 125, and then we're going to keep adding to it. We're going to add 1 to it, and then we're going to compare to 127. So our 127 being the highest 1-byte number we can store with a signed value. And then if it's lower or equal to 127, we're going to jump up to this repeat label. So we'll just keep adding 1 to it as long as it's not too big. And then when we don't take this jump, we're just going to flow through to finish here. So let's think about what this code's actually going to do when we run it. And there's some slides to help us think through this. So AL, we started out at 125, which in hexadecimal is 7D. Certainly that's up near the highest value we can store in a signed byte. We add 1 to it, so that takes it up to 126, 7E. We compare it to 127. Well, 126 is less than or equal to 127. Even though those are up near the top of our range, we convinced ourselves last time in our previous lecture that the way the conditional jump instructions are implemented, they'll work for any values as long as those values fit in a signed byte here or a signed word for if we were doing word size data. So this should work fine. It's going to jump back to the start of, or jump back to the add instruction. And then we're going to add again. That's going to take the 127 up to, sorry, 126 up to 127. Then we're going to compare that to 127. 127 is less than or equal to 127. So we'll jump again back to the start or back to the repeat instruction. And then we add 1 to that again. That takes us up to 128 or 80 in hex. We do this comparison. We got 128 compared to 127. Well, that's not less than or equal. So you might think we bail out of this loop. The problem is, well, 80, if we look at it in hex, and we're thinking of that as a signed value, then that high order 1 in that 8, remember 8 is 1000 in binary, so that is a negative number. And a negative number is definitely below 127. So it's still going to be judged as less than or equal to 127. So we're going to run back to the top of the loop, and we've just written an infinite loop here. Now you might say, how do you know this is a signed value? It doesn't say anywhere. It's not stored in a variable. There's no comment describing it. The way I know is that instruction right there. That JLE is a signed test. So even though the add and the comparison don't say anything about signed or unsigned, this JLE instruction is going to do, or it's going to do a jump based on a signed comparison. And for a signed comparison, this 80 in hex is going to look like it's less than 7F in hex. Again, this 80 is really going to be negative 128. Is going to look like it's less than positive 127. Oh, one more, just for fun. And just as a warning, I think I got this wrong when I thought through it when I was preparing for class. So here we're moving a biggish number, 253 into AL, into the 1 byte low part of the AX register. Then we're going to increment AL, and then as long as we didn't get a carry, we're going to jump up here and increment again. So we're going to keep incrementing until we get a carry. And remember that carry indicates unsigned overflow. So it looks like we're using AL as if it contains an unsigned byte. That makes sense because we're starting it out with a positive value here that's big. I mean, the way we wrote this, it's bigger than what a signed byte could hold anyway. So we're starting it out with a value that's up close to the biggest value we can hold. We increment, and then as long as there wasn't a carry, we increment again, as long as there wasn't a carry. So it seems like this is going to keep getting bigger. On the last iteration, it's going to be 255, the biggest unsigned value we can store in a byte. We're going to increment that. The 255 is going to overflow to a 0. And then it seems like because of the overflow, we're going to get a carry. So this jump on no carry isn't going to happen and will fall through. But I had to try to sell that lie to you because of a detail that I left out. And it's something we mentioned before. You may remember the increment instruction doesn't set the carry flag. And the reason for that is we talked about how, well, that way, if you were doing multi-digit addition, you could use increment to move from one digit to the next without that messing up your carry flag. Well, here, it's going to break this loop. The effect it's going to have is even if AL has 255 in it, you're going to increment and you're going to go back to the start. Actually, even that I said wrong. It's going to depend on what your carry was before this code even starts running, because the move instruction doesn't change the carry. The increment instruction doesn't change the carry. The jump instruction doesn't change the carry. So whatever you did before you got into the loop will decide what happens. If the carry was 1 before you got into this loop, it's going to go straight through and just do 1 increment. It won't run any additional iterations. If the carry was 0, well, none of these are going to change it, and this will become an infinite loop. And I've spent all of my time, but I've also spent all of my slides. So that's all the stuff we were supposed to cover for today. That stuff at the end is hopefully to help you get ready for the exam you'll be taking, to kind of think critically about the instructions we've talked about, including some details like the one we just covered with the increment instruction. Let's call it a lecture, but as usual, I'll hang around if people have questions afterward.
Thank you.
All right, have a good weekend.
Thanks. Have